All right, we're starting, and I'm going to try and make this quick because I'm probably going to do some teaching in class. I thought that went pretty well last time. This class can't be totally you working problems, even though we kind of work them together and things like that. I think you need a little instruction during class, but so far it's been working really well. I've liked it. But now we're starting dynamics of uniform circular motion. And what we mean by uniform circular motion, here's the key to it. We're going to go around in circles. A little Billy Preston action here. All right? But we're going at a constant speed. Why do I say speed? Because the direction's always changing, so therefore we feel an acceleration. So therefore the velocity is constantly changing because the direction is constantly changing. And it's always pointing towards the center. In other words, there's a tension in this rope that's going this way and also pulling back this way. But the tension caused in the rope, there's two actually here. One is there's an acceleration due to gravity going down. In other words, if you don't have a motor on this thing and you try and spin something over your head, you will not get it to go in this type of motion. All right. In other words, if you're standing here and you've got something that you're trying to spin around the top of your head like this, you can't do it this way. You cannot do it this. I mean, watch the rope turns. This is impossible unless this thing has a motor. Why? Because it's actually when you spin something, if you hold it up over your head, it will spin like this and around the front of your body and then around like this. All right? Because gravity's pulling it down too. But it also has a tension going this way and an acceleration going straight into the center. All right? Now, so if let's say you're going in a uniform speed, what is your speed as you're going around a path at a uniform motion? All right. Well, it takes you one time period to go around that. Let t be the time it takes, and that's capital T, and we call that the period. All right. So a little bit of. So when we meet tomorrow in class tomorrow, t is the period. That's time of one lap. That's the time of one rotation. When we get into rotational dynamics, which I'm going to combine chapters 7 and 8 because they kind of go hand in hand. All right. We're going to attack chapter 6. We'll do 6, 7, and 8 kind of combined, and then we'll get into 9 and 10. And 10 ends with waves and stuff like that. But anyway, so there you go. Time of rotation. All right. So V is equal to 2 pi r, that's the circumference, divided by t. And that's your rotation. All right? So it's 1 over t. We also call it, so V is equal to 2 pi r over t. We also call this V equals 2 pi r times the frequency, where frequency is equal to 1 over t. Where the frequency is equal to 1 over t. In other words, if you have a 33 1/3 RPM, that means you go around, your frequency is 33 revolutions in a minute. If you divide this by 60, because times 1 minute divided by 60 seconds, 60, multiply this by 60, 60 per 1 minute. That doesn't make sense. Oh, it's because I'm screwing that up. 33 1/3 revolutions per minute. All right, so I got to multiply by 1 minute. I knew I was doing it right. Divided by 60 to get my 60 seconds. To get my revolutions per second, that's your frequency. Okay? So if I take 33.33 repeating divided by 60 seconds, that's my frequency. And my period, which is measured in hertz, which is seconds to the -1, then my period is equal to 60 seconds, divide the minute divided by the 33 rotations it does in that minute, and that gives me the time of one rotation. That gives me t, which would be about 2.7 seconds. Right? All right, so that's what, now, those of you in biology and things like that going into medicine, or anytime you use a centrifuge, they rotate about 12,000 revolutions per minute. Okay? All right, or 2,000 revolutions per second. Okay, so here we go. One revolution, da-da-da, self-explanatory. All right, in uniform circular motion, the speed is constant, but the direction of velocity is not constant. This is what I was talking about. So it keeps changing. All right, so they kind of try and do a little algebraic calculus here. And so our our uniform acceleration is equal to v squared over r. It's one of those things, just trust me. It equals v squared over r. Okay, I'm going to stop there. And then we'll look at what your first group of homework problems might look like. It's not that big a deal. I mean, it's not that hard, and then we're going to look at centripetal forces and things like that.